but I'm glad you can all attend, and thanks also to Colin for inviting me along. Let me just fire up the presentation a second. Here we go. Can you see that, Colin?
Yeah, we can see that fine, Darren.
Lovely, brilliant. So this really follows on from an article I did in the PWI journal over two parts on switching crossing inspection, looking at from sort of the manufacturing side right through to the maintenance side. So it's the whole life of S&C. Just a little background about myself. So I'm chartered, 32 years railway experience, major projects, renewals, maintenance, also reliability of S&C as well, and some product development for reliability. Principal switching crossing engineer for London Underground TfL. Worked also with New York City Transit and PATH, that's Trans Hudson Railways, on switching track reliability. Also some product development and product approval for S&C in the UK as well. And currently I'm working part-time with Network Rail Technical Authority on sort of sleeper strategy and composite sleeper work, and also working with Balfour Beatty and Transport for Wales on the Cardiff Valley Lines project as well. So let's just kick off by looking at what our current S&C inspection process is that we use in the UK. And I say the UK because this is sort of mainly governed by the UK processes and standards. So pre-installation, we generally tend to do a quality inspection form. Sometimes the supplier will do that for us and the installer may then witness that inspection form. We do a design verification survey, so we basically make sure that the S&C design fits, it ties in, there are no issues with it tying into the sort of the boundary works, if you like. And we also do a dilapidation survey. So lots of information and surveys and reasons to access the track to get that information for that sort of pre-installation. And at installation, we then have the sort of S&C quality installation form. So not everyone adopts this, but it's basically a cut and paste of what you would do when you inspect in the yard at the prefabrication inspection. It ties into the inspection test plan. Inspection test plans can be detailed to go into more detail for S&C and generally are, certainly for temporary works and so on. And installation, we also need to look at the sort of the TRV in terms of sort of the quality thresholds and what the geometry is doing, have we achieved what the design is supposed to do. And then there's the as-built surveys, which just generally tend to be sort of tolerances to design offsets. In some cases, they may be a full geometrical file that you can hand over onto a GIS model, or they may even just be slews and lifts of the remaining track. You know, some cases we can not monitor, but actually permanently sort of locate the track with other monitoring devices so that people can see where the track should be. So we could sort of permanently mark it in some case. And then under maintenance, so handed over into maintenance, then starts the sort of inspections for supervisory inspections, the 053, 054 inspections for switches and crossings. Yes, TRV is an ongoing thing under maintenance that we keep an eye on. A rail defect register that we then look at, especially in S&C, we'd then go to look. And then you've got your sort of basic visual inspections from the patrolman. So our current S&C inspection tools we use, so prefab, we would probably use a 3D Trimble coordinated survey. So some of the suppliers use this. Some suppliers may just use a string line or a baseline to actually measure the alignment. So if you see that picture there on the third one at the top, there's a string line down the side there. So there'll be offset measurements from that string line to make sure you get the alignment. So quite an ad hoc and old way of doing it. Some suppliers may do, like I say, 3D Trimble survey of the full layout. Amber trolleys can also be used to run gauge through. So if we want to do a quick gauge run rather than dropping down every bearer and taking a gauge measurement, we can use amber trolleys to do that. But then there's the usual 4-foot gauges, feeler gauges, steel tapes, all those other things that we use. And sort of looking forward, you've got that picture down there on the bottom left-hand side of Luciani Felix. So the Felix S&C inspection trolley, that could be used to do an S&C inspection. We've got the drones, that's that picture there, the second one in at the top, drone inspection, which is one thing I'll go into in detail later. And then there's also sort of 3D trolley scanners as well that we can use. And other things we've started to adopt is using lasers for sort of toe measurements. So that's sort of picture on the right hand side there for aligning the toes and making sure the toes are correctly aligned. So just going on to the drone surveys as part of Network Rail's work with Intertrack 2. In work package 2, we looked at drone surveys. So we're looking at to replicate a basic visual inspection to what the patrolman would do, and also looking into sort of supervisory inspections where you go into more detail measuring gauge and openings and so on. Some other additional benefits we did look at were prefabrication inspection and also turning that 3D model into a digital twin for BIM. So a bit of background to the drones we were using. They were supplied by Plowman Craven. They had to do the full civil aviation permission, which they do for Network Rail. They want a call-out contract for Network Rail, so it's just part of that call-out that they were able to supply 2 different drones for this. And the reason is the main reason for bringing and introducing drones is boots off ballast. It's not putting people into an unsafe condition and place. So let the drone do the work, and then let the drone do the videoing and measurement. And it's also seeing how accurately we can measure with our current technology. That's sort of one of the biggest that's the questions that we were sort of trying to answer. And the elimination of sort of possessions and the access requirements as well, and line blockages. And really sort of there's an extended range of, sort of added value for the product. So it's like how you can use within sort of the 3D point clouds and orthographic and photographic and different types of data you can use and data sets you can use with the drone. They are quite susceptible to rain and to darkness. So we did find that. So you do need some sort of fairly clear weather conditions. So we started off with two trials. The first trial was looking at the basic visual inspections on existing track, and then we did a trial within the sort of VAE yard. So this table here it details the inspection types we looked at: the basic visual, detailed supervisory inspection, that's following the TEF forms that we do, layout prefabrication, what we would do under layout measurements and inspection forms. And then we just thought we'd look at the 053 and 054 to see how accurate we can get it as well. So it wasn't one of our aims, it was just how far are we away with the technology. So the VAE yard trials were done up in Harworth. We did initiate a BVI there as well, sort of an unobstructed, if you like, because there's no ballast surrounding it. But we mainly use that to do a sort of detailed supervisory inspection form using 3022 and 3068. So we can do a comparison between what we measured with our standard tools versus the drone, and then a layout prefabrication measurement. So using tapes, using total stations, and sort of doing that comparison as well. And then the 053, 054 was really just looking at from a new cast crossing and a new switch, how they vary and how accurate we can measure those two. So we had some pass-fail criteria. They were based on what we would see in Network Rail standards. Also, it's to do with what the level of, I guess, inspection from a visual point of view, what we'd expect as well. So we put some pass-fail criteria down, and most of that's really is getting those dimensions within what we think is an allowable tolerance. So here on the left-hand side was the TEF form we used, measuring the sort of toe openings and the gauge at the stretcher bars and residual switch openings and so on. We're also interested to see if it can actually pinpoint. So this middle picture here of the switch, the actual toe position is one small thin piece of steel on the upright there, and it's marked on the stock rail, but you can't rely on that. And then there is the vertical sort of 165 mm long. There is that position there that you can measure from that is more accurate. And then again with the nose, if there's no marked nose position, where do you put a tape on that slight that area there where the nose actually is? It's not I think a repeatable measurement in terms of where it's marked. Some suppliers may put like a weld collar on the side there, or a sort of a slight bit of raised flash arc welding there to give you sort of the position of the nose, so you can measure it in the future. But these things aren't very well marked up, and we measure toe to noses quite accurately, and if we don't permanently mark them up, we can start to lose those if we're not careful. So we set up a survey control on the ground using total stations and control grid for the drones. We trialed 2 drones, a Vogel and a Falcon 8 drone. This was to capture data of varying quality, varying heights, 30 meters, 20 meters, 5 meters. We tried to fly the drone at. And then this would enable a decision really on the sort of quality of the data, sort of for BVI and for the supervisory inspections as well. The ground sampling distance here was 1.6 mil and 0.9 mil. So that was captured by the flying drone. And so ground sampling distance, or GSD, is really the it's the measurement, it's the distance between the centers of the 2 pixels that you're measuring on the ground. It's not the accuracy, it's actually the measurement on the ground of what you are measuring between the 2 pixelated points. And you can see there we did have some our toe to nose dimensions and nose to nose dimensions. So we're quite accurate with some of those. But if you ask someone to do something with a tape and then ask someone to do something with their total stations, you'll still find that they'll have errors between them as well. So when you're comparing sort of different measurement tools and techniques, it is difficult to say which one is the one that's most accurate. I'd say here total stations is very accurate, but a tape over a small distance is also accurate as long as you place it in the right place. So we were quite happy with those results from the drone. On top of that, we also developed the 3D Ortho Photos. So this is basically an S&C digital twin. These images you can manipulate, you can analyze, you can measure, you can flip them around to all angles where the drone saw. The drone was flying at an oblique angle to gather sort of 45-degree angle of sight, and then vertically down, and that's where you sort of stitch that into the point cloud data there. And you know, for post inspection, so if there's something you missed, you can always rely on these images to go back to. If say damage occurred on track and you thought, did we see that in the yard, you know, where did that come from, maybe we missed it, then again this is another opportunity to go back and measure. Whereas once it's been taken away and disassembled, then you can't really do that. So it's that you know, that recorded evidence really. So on the TEF forms and the supervisory inspection, we followed the standard measurement locations where you would take measurements from. So here we've got that comparison, we've got the on-site value, we've got the value that we took from point cloud data from the drone, and there's the difference there. So you can see a lot of it was 1, -1s, 2 mil, so we're not too bad, -2. The worst one being 4, and that's A2, so that's gauge at the second stretcher bar, and we know measurements at gauging at second stretcher bars, it's within that machined area, so it's quite difficult to replicate. You've also got to get the drone to actually, you know, measure that 14 millimeters down from the rail head onto that sort of inclined rail surface as well. So that inaccuracy that can be improved upon by having sort of certain set locations to measure at, but we do tend to ignore those measurements in some cases, and we use a back-to-back measurement along that sort of along that area. And we know a back-to-back measurement will be within 1 or 2 mil because they're very precise, and the locations where you measure those from you know, are very repeatable. So yeah, so from a supervisory inspection, 2 mils, 3 mils, on average something like 1.5 mil. So we're getting within that 1.5 mil area. And on the basic visual, so this was done at the Mantle Lane. It's an old turnout installed in Colville. Myself and Phil Winship, we walked through and did a BVI ourselves. We noted down the bearer numbers where these observations were. We then marked up all the bearers and let the drone do its work, and then we analysed the drone footage on the 0.94 and the 1.6 ground sampling distances, just to see if any of these could be observed. So as you can see here, most of those could be observed. So sand present on the slide plates, rusty, worn slide plates as well. That was observed by the drone. Check plate broken, crossing rail pad slipped out. So again, all of this was observed. There was a slight crack on the sort of point and splice rail joint, and the crossing had a chip, but only the 0.94 could sort of pick that up because the 1.6 ground sampling was slightly blurred on that. But everything else was picked up fairly accurately. Another thing we checked with, and this is with Plowman Craven, they developed for us for cant and gauge. We weren't too concerned about cant measurements at this stage for these type of inspections, but gauge we were. So really it's making sure the drone is picking the measurement point correctly, accurately and repeatably on the rail, because it's 14 millimeters down, it's not on the top of the rail head, it's on the running edge, and there are all sorts of other imperfections in the sort of photogrammetry that you've got to overcome when you start to look at these images. So they developed this algorithm that could sort of basically take out that noise, look at it. It's, you could call it a line of best fit, but it's got a bit more background to it than that, and it's taking away some of those areas that could be there, because it's either seeing a slight shadow, a slight reflection, or it could be something that's not actually, you know, the actual contact surface of the rail. So this then got us the gauge within 2 mil, I think within 1.5 mil of what was measured. We were able to get, and this was at 20 meters and 40 meters. So that rail string extraction algorithm, so it was improved several ways, and it's, you know, it's looking at the height of the rail string. So it's using the cloud data to analyze the rail string, and then they applied this approach then to make sure they can get a better sampling patch and better data through it. And allows them to sort of enable the outliers, and then they can sort of start to give a more accurate representation of the gauge itself. So on the crossing wear and measurement BVIs, so the remote BVI did detect the wear on the nose on the 0.9. There's a 2D image we were able to get from the point cloud. So we were looking here for an 054. You could probably see some areas where you see maybe lipping or stepping in some of the wing rails. But as you see here, it's a very hazy image. When we started to measure on that, we could get it to something like 1.52 mil. Again, not enough for an 054, but it could be enough to sort of initiate something for you to say, I can see a problem there, I can see some uneven wear. You could even do, you know, relationship between nose and wing rail without step height, you know, and if there's something there that, you know, does draw to your attention, then you can also then raise, you know, a more detailed 054 inspection from that. So this was more an add-on, if you like, from the continuation of the work we did with Intertrack 2 and the work we were doing on drones. Pictera contacted, and they are a pattern recognition specialist based in Switzerland. They contacted Plowman Craven and said, we've got some software that we can apply to your photogrammetry, and we can do some sort of pattern recognition analysis on your work. So they built the detector model. So we provided this imagery to them, the 0.9 imagery, ground sampling distance. They did, the first part there is area training. So really you need to teach the model what to look for. So it's the clips, it's the bolts, it's the sleepers, it's all those sort of critical parts that you want to make sure are there and in place. So they just did a very basic one for now. They took that training session, then they applied it and they checked it. They then run the detector model over the imagery, then they can see some of the problems, you know, where you would expect to see a clip and there's no clip there. So they identified sort of across 3 images within 3 seconds that there were clips missing. So these are a multiple of detectors here. So the one is the sleeper. So you can see sleeper, uneven sleeper surfaces. That could be a crack, a split, or a dip, or cupping. Then 2, you've got the chair screws. 3, you've got 3 is the sleepers, and 4 is pan roll clips. So you can have all 4 of those. You can have 6. You can have multiple of different sort of pattern recognition or samples that you're looking at to detect. And what I'm going to show you now is, let's see if this works, is some work that they did to, just going to stop sharing this and share this again just to make sure you have got it, because sometimes it doesn't. Right, can now someone tell me you're now seeing a different screen?
Yeah, that's
Yeah.
fine, Darren. Yeah.
Thank you. Cheers, Colin. I didn't want to get lost on my own. So what you're seeing here is an image. On the left-hand side, you've got the Plowman Craven survey from February 21, and on the right-hand side, you've got the one from September. Now, by zooming in onto this, and I'll do that now, I can go down. I'll show you the level of detail I could go to. This is the closest it gets. Okay, so very accurate. And what I will also show you is, I'm going to zoom out. Apologies if all of your screens are starting to go blurry. Let's go into the switches. Let's go into the critical part. So if I just zoom in, keep that marker there. If I zoom in here, if I zoom into the stretcher bar, and I can show you here how accurate we can see. So I can see a face of a nut there on that bolt, on that stretcher bar. And we know these have got a tendency to loosen on some of these designs. And so by just putting some witness marks or indicators in there, we could actually use this evidence to show if anything's moved. So what I've got on the left is, again, as I sort of scroll from left to right, on the left, there's the stretcher bar there. As I go onto the right here, so that's the image there in September. I could do a cross comparison between the two. I can actually check to see, has that nut actually moved between the two? Very, very slightly, but that could be a shade thing. But if you had marks on there and something more identifiable like witness marks, you'll be able to pick that up really easily. You know, you could even go into the toe and you could say to yourself, right, this was a warm day, this was a cold day, has the toe moved? You know, and it hasn't. But you can do things like that. So has the toe regressed back? Has it extended? The other thing it's showing here as well, if I go back, you see all these hazards here. So I've got a hazard. It's actually identifying a problem. So let's see this one here, this little hazard symbol here. What's going on there? So there's a clip there on the left-hand side. Right, I don't know if you can notice this, but it's actually someone's, well, between the two, the clip there was slightly out. Let's see which way the clip's going in. It is going in that way. Yep. And here, someone's actually put it back in. So that's good. But it has indicated that it's moved. The clip's moved. Now, this one here, as you can see, that clip has actually moved out. So it's moved outwards as well. So, and in some cases, we've got identified areas where clips have actually fallen out completely. If I can find one, I'll see. This may be one of them. I have to zoom in. So that clip's moved out. And let's try one around the crossing. Oh, here we go. Yeah, so on the left-hand side there, if I show you the left-hand side, the clip is in there. When I go on to the right-hand side, the clip's broken and on the floor. So that clip has come out. So yeah, quite a powerful tool, you know, for analyzing between two different sets of data. And again, you can go into crossings, you can go into joints, you can go, it's also, so some of these eyes here for information, you can sometimes zoom in and it's picked up on something's moved. And I'll tell you what that is. So on the left-hand side here, there's no vegetation. On the right-hand side, the vegetation started to come in. So it's picking up that vegetation is starting to sort of come in. And also with other things like cans and litter and those sort of things, it picks them up. If they weren't there before and they're there now and they shouldn't be there, it's also telling you that there's a problem there. So yeah, that's where we got to with the pattern recognition work. Let's go back onto the slideshow. So that really does complete our work with Intertrack 2. For Intertrack 3, Phil is extending some more work on this. There is some other uses we can expand it to. One of them is looking at track movement in terms of buckling, looking at ballast profiles, looking at whether you've got a regulative ballast profile, whether the track has moved, and also looking at sort of thermal imagery to see, you know, temperatures of ballast, temperatures of sleepers, temperature of rail, and how that sort of dissipates along a section as well. You know, like putting a thermometer down, you know, you're relying on the thermometer at that sort of particular point, but we know there's shade, there's all sorts of different areas of the rail that it's difficult to know just from one thermometer. So this is, you know, this is full coverage of the temperature of the whole track system, looking at it from that perspective. And then you could also you can monitor track movement and look at sort of profiles. If ballast profiles are moving, if the ballast profile isn't conforming, then you need to do something about it. So that's sort of putting some triggers, if you like, into sort of I guess track buckle areas and some of the hotspots that we know cause us concerns. So that's the drone work. Let's now going back to the article and some of the areas that we sort of touched upon. So in terms of prefabrication inspection, you really need to consider the type of layout you're inspecting. So if it's just a standard bearer layout, if it's a modular tie plated layout, or it could even be a direct fix layout. So it's a single rail support, something similar to a Sonneville block or a Delcor direct fix system, or it could even be a complete track slab, a prefabricated track slab. So you've really got to understand what inspection criteria do you apply to each type of track construction in terms of S&C. So most of it is very common and you tend to do a rail plate inclination. You wouldn't do that on anything with bearers, but where you've got a direct fix, you've got to think about each rail is independent. It hasn't got a set inclination. You've got to set the inclination, you've got to set the gauge, you've got to make sure that a prefabrication, all of that is actually being constructed as it would be in the track. So you may need to use dummy bearers to fix the track down and screw base plates down so that they can be inspected. In terms of the POE, so yeah, you would check the POE in all of them, but it's a lot more important that you do a POE check on a direct fix layout, because again, you've got two independent rails, you've got rails that are twisting and doing different things because they're not fixed coplanar. And you need to measure, and you wouldn't normally measure cant on a sort of beared layout, but on a direct fix layout you should, because there could be some issues there with the rails not actually being supported correctly. And then with that, you could also measure the rail inclination as well. Fixed heels and front squareness, well, we do sometimes do that on some of our bearer layouts, but it's a lot more important on, again, direct fixed layouts where you've got independent rail longitudinal support and longitudinal placement. Heels can be out of square. You can't rely on anchors holding the stock and switch rail in place with a bearer, and the bearer being square. You've got base plates floating around. So all those areas that you normally fix down on a bearer, you're now floating with a direct fix system. Gaps in construction, so gaps between base plates, between pads and areas like that. You need to look for those, especially if you're doing a direct fix as well, because those can come back, and if there is a gap there for some other reason, then that gap will always exist and you could have problems in the future. Build-up accuracy from the rail plane and construction height variance, again, very important. Orientation markup is important on all of those layouts, but it's marking up which direction certain parts would be. Rail support clash check, it's a big thing that we do. So this is the support system you might use to, like the jigs that you would use to support the stock and switch rail. You need to make sure it doesn't clash with something else. There could be a cable, there could be a stretcher bar, there could be a conductor rail ramp, there could be something else that's there. You almost have to do a 3D image clash, and we've done this previously for some jobs, to make sure that your jigs aren't clashing with other items that are being installed at the same time. The same goes for third and fourth rail checks as well. And one thing at that bottom there is the free switch test. It's not really a network rail deployed test. We do it on London Underground, and it's really to pick out to see if the switch has been overcurved, or if there are large gaps between the sort of stock and switch when it's sort of manually closed, just under normal sort of pressure that you would apply to the switch. If it's been over-crowed or under-crowed, or if it hasn't got the right curvature to it, then it's going to pick that up, really. So that's with no stretcher bars attached, completely free. And you can also tell from that if you've got a vertical switch. So if you've got a vertical hump or hog in the switch, because some S&C can actually pull some rail down and can hold some rail in place. And when you release it from the stretcher bar or the drive attachment, it could fly up in the air. And then you'll know you're always fighting those forces by using the point equipment to do that. So it can also pick up those things as well. It also tells you what your natural flangeway is with no back drive, with no primary drive in place. You bar it open, you can actually measure a natural flangeway. So it's actually a good way of verifying if we do something like an FML or you do a switch flexure analysis to see how much flexure you have in a switch. you can use this to sort of verify that data and to test that, yes, you can get a 50mm flangeway with 150mm opening, you know, on a D switch. Or so it gives you, you know, gives you that added benefit as well. Other parts, I guess you've now done the prefab, you're installing it, but what happens when you've got to hand it over to the signals team? You know, the signals team really want to know that you have installed it, you've installed it accurately. You haven't just gone to your standard tolerances. You probably need to think about going to finer tolerances, and you need to sort of home in around the switch area, you know. So things like confirming the track alignment is within plus or minus 5mm between the stock fronts and the hill, within 5 meters of that area, you know. And if you've got some variation in that, if you've got a +5 and a -5 and it's near the toe or the heel, the switch isn't going to fit up, and you're going to have issues there, and they're going to have to sort of get around it somehow. So you need to make sure you've got that alignment, the cant, the gauge, all of those tolerances at a finer, what I'd say a finer tolerance than you would normally do for the rest of the layout, because the switch needs to have that finer tolerance to work to. Otherwise, you're masking a problem, or you're creating a problem further down the line. So you generally do these inspections with the signaler there. They're about to set up their point equipment, and they want to know that they've got the gauge, they've got the other, you know, the setup is correct, and so on. You know, they'll try to sort of set something up and then find a problem, and then they need to bring the tamper back, or you need to do some localized packing because you can't get the vertical. And one other big important part is towards the bottom here is the stock to switch rail fit. So we're measuring at every bearer, so it's more accurate. And we're also looking for the gaps between the switch rail and the slide plate. So measuring at every slide plate and making a record of that, you know, to make sure it is within 2 or 4mm, or anything that's, you know, making sure there are no large gaps that are showing that the rail is either being held upwards by a high plate, or there's a dipped section somewhere that needs to be lifted up. In some cases, that could be beyond the switches. It could be in the fronts. It could be at the back of the hill. It may not be in the movable section, but that could still be affecting the vertical position of that switch rail. So you need to sort of think 5 meters either side as well, as you do with horizontal alignment. And then you have the TEF forms that we use for sort of, you know, this is an in-bearer clamp lock version. So it's a handover certificate where they take measurements as well. A lot of measurements there are taken by signals and track, and it's the same measurements. So you're talking flangeways and RSOs, the rear stretcher bars and so on. They're sort of your key measurements, and switch squareness and all those other things as well. But this form really is a way of, you know, you can inspect it together, sign it together, and then you can make sure, yes, it was done as a team, not hand it over and just expect it to work. So it's making sure you've got that reliability from the start. Some of the problem areas. So when we've installed S&C and then we start to go in and we start to think, if I'd known this problem, I would have done this differently. You know, so what I've listed here, fortunately, the Excel sort of spreadsheet goes further down beyond this screen, but what I've listed here is sort of there's the component areas or parts and some of the issues that have been observed, and then the countermeasures that we've had to adopt. So it's more of a lessons learned, really, of all these different, whether it's a bearer layout or a direct fixed layout. It's all the lessons learned, I think, over the probably my last 20 years in installing S&C, maybe longer than that, but just things that, where there's been a problem, how do we get around it? And how, you know, is there a standard that follows this? Is there guidance? Have we instructed our people? Is everyone aware of it? You know, so things like cant measurements being taken on the nose topping. I've seen trolley measurements go over a nose and they say your nose is 6mm down. So where did you measure it? Oh, just there. I was like, well, the nose has got topping on it. You can't actually physically measure the cant on a nose. If you go just back beyond it, you may get a measurement. So it's making people aware of that, and that could be the surveyors that use the trolley and use the data, and you know, or it could be track engineers that are using track gauge but just aren't aware that you can't get an accurate cant gauge reading at the nose. Crossing V base plates installed with room within the seat or field side. So you install it in track and the rails push out, and this can happen on plane line as well, but in crossings it's very common because you get high lateral forces on some of the curved crossings you have, and that's where you start to see it widen under load, and then before you know it, you've handed the track back and you've gone you've widened gauge. And that's because some of the base plates we use have got a lot of wriggle room within the housings, and we use sort of that VA/VB range where we know we've got that ±4 in some cases, and we pick the nearest one that will hold the rails to gauge, but it could be the sort of the top end of the tolerance. You know, we could have the bearer slightly pushed forward or back, which could be squeezing gauge or widening gauge as well. So there's those sort of issues there you need to think about. I've seen tampers go in, move crossing base plates and affect gauge by 5 mil by moving it by 100 mil, and the whole bearer's moved up. You know, so there's things like that you need to consider as well with the bearer spacing and squareness. I won't go through all of these. Again, it is in the article, and a lot of this information will be on this presentation, and I can share the slides with people as well. Things like excessive spring, twisted slide plates with and without POE fitted. You know, you've got to look at it with and without. Ball and claw not central. Surveyor's measuring gauge prior to POE install. We know that one, you know, so really there could be some residual opening in there, but the idea there really is to use a back-to-back gauge. Stop fronts not square or incorrect to the longitudinal positioning. So there's many things there. So really this is just a guide for people to look at and say, right, okay, maybe I can adopt my ITP to make sure I cover this or train people. And again, we've actually done some training on this with London Underground previous to this, and we've actually gone through these issues, and we've provided a sort of training pack to people to say, this is what you need to look at. This is how you measure it repeatedly. This is how you can record it. And if you need to adjust it or do something, here's some guidance on that as well. So it's making sure you've got it right first time, because most reliability issues come from a poor installation where something's introduced at installation and forevermore will be there unless you can actually correct it. And the correction methods sometimes aren't a long-term fix, and that's the issue, you know. So there's more here, modular tie plates as well, concrete bearers, conductor rail for all those third rail and fourth rail enthusiasts. POE, some issues there about POE installation and handing of switches and crank handing and stuff, stretcher bars and so on. So yeah, again, I won't go through all of these in detail, but do refer to these, and it's in the sort of previous article as well. So we've now handed back to maintenance, and we've sort of looked back and said to ourselves, okay, we've done a lot of measurement, we've done a lot of analysis, we've done some design, we've got a lot of documents here. How do we make sure that this isn't lost? And what is it that we want from the future that, you know, can provide all this information? So, you know, everyone's mentioned the word digital twin. It's similar to BIM. But in terms of an S&C digital twin, these are the sort of inputs you would expect into providing a digital twin. So I'll start off from the bottom left-hand side. So starting off with the design phase, really, you've got your 3D design models, and that's also the switch and crossing profiles, you know, so having a 3D model of the switch and crossing, so you can analyze wear from that. And even the POE and the POE parts and the whole inventory for asset register for everything that was designed and supplied at the prefabrication. So there's an example there where you can actually use the drone 3D model as the 3D model that you use going forward. Or you do another 3D model once it's installed and say, yeah, we're happy with this. Let's reset the baseline to this installation because it matches pretty much what was at the yard at fabrication. And it's the best we'll get. So let's use that. S&C system, so the O&M manuals for the S&C system, not just parts of it, not just a stretcher bar, not just a point machine, not just the rails, but the whole system. How does it work together? When you adjust the stretcher bar, you adjust the gauge, you adjust the toe opening, you adjust the flange area, you adjust, you know, the signal setup, you adjust. So it's making sure all, you know, both signal and track aspects are covered in that, in terms of tools, training, competence, skills, and all of that. Signal and track. So now we're going into sort of the signal and track failure data, maintenance history for work undertaken. So we've got reference to any of those data, so any of that data for failure that we can rely upon as well. Then there's a degradation model. So these degradation models can be produced way out in advance. If you've got a standard set of S&C like an FV turnout, FVS turnout, then you can say, okay, there's a degradation model. You would then plug in its duty, whether it's tonnage and its speed, and then you can have some form of a degradation model that would help you predict the frequency for grinding, welding, parts replacement, So you've actually got dates when you say, right, you need to change the crossing within 15 years. The POE adjustment needs to be done 6 months cyclical. The tamping needs to be done 5 years cyclical. Actually giving it defined maintenance interventions for when they need to do this work. And also it can predict from that degradation model, it can predict residual life, either as the whole system, and that's what it is. It's got to be looked at as a system, because if we start designing things separately, then we're going to be replacing things separately. And when that part is the ballast, then you haven't got a system that's working at the same level together. The asset condition monitoring data, so anything from the point machine asset, RCM, remote condition monitoring, points heating, digital void meters. So you may want to apply some sort of track-based measurement systems, accelerometers, track-mounted sensors. So you could use something like an embedded sensor or a track-mounted sensor, similar to the Conux sensor that you use, where you can actually fix it to the top of the bearer, and it can tell you, how it's actually under traffic, how it's the vibration and the movements, and there's other sort of sensors we can use as well in terms of sort of fatigue and so on. And we can set up alerts as well, the sort of reliability thresholds for that as well. Weather conditions can be overlaid onto this as well. And really you are looking at a combined diagnostic tool, whether it's on one big desktop or one big sort of user interface that you can use on the dashboard, and all the information is talking together to tell you, that and that means this. Then that's what you need for S&C. At the moment we look at RCM and we go, okay, we've got some traces here that the alarms are coming up because it's high friction. What's going on with the track? We have to send someone out to look at it. But if we said, oh, well, I can tell you, actually, my void meters are showing a 10 mil void, and I'm also showing some high acceleration in the crossing and the switch area. Right, okay, so now we've got an idea where this is sort of leading to. And again, if you can have a precursor to that saying, okay, if the acceleration or if the voiding gets to a certain amount, you are going to see the point machine starting to fail as well. So the two precursors can be used in that way. Dynamic measurements. So if we're using systems, train-borne systems from track recording vehicles, rail condition monitoring, pattern recognition, having rail profile measurements measured dynamically would be really good for this as well when we get to that sort of stage. And then you've got sort of geographical, topological, so you can look at alignment, you can also look at even cuttings and all the other issues as well with that. And then in terms of sort of the static gauge measurements that we do, and also other dynamic measurement systems and so on that we could use and sort of employ on this as well. So including Felix. So you could use Felix as one of your measurement systems that you can feed into the S&C digital twin, because that can use profile data and it can analyze the sort of nominal or absolute profile of a crossing or a switch against that warm profile, and it can tell you how far is it before we need to sort of interject and do something with it. So when you sort of consider those two types of measurement systems, so there I was talking about sort of static measurement systems we use a gauge or something that's unloaded versus sort of the dynamic measurements. It's good to know the difference between those measurement systems and what is it you actually want. What is the measurement or the measurand that you want in terms of is it the correct method? Am I seeing what I need to see in terms of safety and reliability? Is it better to see it statically or is it better to see it dynamically? So this table, these next two tables, are really looking at those sort of key measurement areas, the gauge within the switch panel, the flangeways, the toe openings, and so on, and whether it's best to measure it dynamically or statically. So in terms of gauge within the switch panel, well, I've got the green basically shows that is the preferred method. Yes, and we do it in both ways at the moment. So the yes means yes, we do it currently in those methods. And we do like to see it dynamically because rail spread. So that's an obvious thing. Flangeways. Do we want to measure a dynamic flangeway? Well, flangeway spread as well, but that means that if they do spread, it's getting contacted. If it's getting contacted, we don't want flange back contact. So in my mind, it's better to actually measure it statically. That's because it's not being forced by a wheel and it's not moving by a dynamic means. It's actually what the train first sees before it hits that back of that switch. So a static measurement for flangeways, I think, is a lot more. I guess is where we need to be with that measurement. Toe openings isn't such a safety thing. It's more a reliability of the point machine, so not much of a big concern. Residual switch openings. So again, the train will close it. So dynamically, the residual switch opening will be closed in most cases by the train. So we want to know if there's an RSO in the first instance, because then that affects switch setup reliability for the point machine. It's either overcoming something or it just can't close it. There's too much friction. Something is stopping it. So we need to know if we've got an RSO there. So in that case, static dimensions is better for us from a reliability perspective. Slide plate to slide rail gap. No, so this is a big one. Difficult to measure dynamically, but once the train's on it, it's obviously closed. But again, you want to know if it is sitting in the air, you've got high friction. If a switch is sitting with a large gap between the slide plate and the switch rail, you've got a high friction area where it is actually in contact, because it's designed to be uniformly distributed between all of those slide plates. If it's now only on 3 or 4, you've got high friction at those locations. And most slide plate friction comes at the rear of the switch, where we either don't lubricate or there's so little movement it doesn't get the actual throw and the lubrication, or the actual the metal on metal reaction is different. And also you've got the sort of the toe load of the clip just behind it at the heel, so that's really where all the forces come from, are at the heel. But we operate the point at the tip because that's where the longest armature is, so it makes sense to do it there. But that's why we use back drives, because we need to sort of transmit that force to the heel or to the back of the switch to make sure we get a flange way, and to make sure the effort to throw the switch is evened out along the sort of switch length as well. Check gauges, very similar. Do you want to measure a dynamic check gauge? Well, no, because you could be forcing it, you could be dynamically moving it, and that's what you don't want. I've seen some check gauge move more than 5 mil under dynamic loading before. That, which is quite a concern really. So dynamic movement in some cases can be negligible, but it is, I guess, ray roll under load as well. So then we have back-to-backs and diamonds. I won't go through the rest of them. Switch profiles, cast crossing profiles, and cross levels. So again, read this in either in the article or the slides that I present, that I provide to you afterwards. Then in a case, I guess, where we're looking at pattern recognition, we're looking at how do we automate what is a basic visual inspection? How do we turn that into something that can be repeatable through machine learning, through pattern recognition, through teaching software what to do? So the things we currently do under basic visual that you've got to consider are, we have a tactile approach. We kick things, we remove dirt, we touch surfaces, we stamp on bearers, there could be some grease or dirt covering a defect, so we uncover that defect. For visual accuracy, the eye can see hairline cracks. We can do a visual check on the top of the line. We know visually whether there's a misalignment. We can do a visual check on the bearer squareness. We look at correct parts. So there's a lot of machine learning we have in our own brains that how do we make software do this, in terms of making sure that 200 different parts for a hill block and a bolt system or fastening system are sort of replicated in that software. So parts assembled correctly, missing parts, hold switches. Again, that's the sort of measuring between the stock and the switch and the slide plate. And then some clashing and obstructing parts. We look around in switches for something that might be mechanically obstructed to stop the switch moving, or stretcher bars moving, or litter in place. So looking for sort of those things as well. And then we've got telltale signs that our brain cognitively says to us, right, this is probably the root cause of this. We look at fault combinations, we look at repeating faults, we look at ballast formation conditions, drainage issues, earthwork issues, mechanical damage from visual inspections, mechanical obstructions, and then observing the track under load and observing points moving as well. So we sit there and we watch a set of points move. We can hear it whirring away, grinding away, grunting, or doing something that you just think that's not right, or looking at the switch movement at the front and the back, and you say to yourself, why is the back going up for the front, or vice versa? So there's those sort of things that we do visually, but how do you turn that into something we can do in the future for pattern recognition? So these are just some of the challenges we've got. Some of these answers have actually been addressed. Some of these questions have been addressed in what we do with plain line pattern recognition. but what about for S&C? So there's still a lot to do here, you know, to get something as detailed as what the human can see. So at the start, I talked about the sort of the current, but in the future, the UK practice for whole life S&C inspections. This is how I see this going. I can see 3D scanned layouts. This is partly my vision, but hopefully we'll get there. 3D scan dilapidation surveys, system O&M manuals, asset management regime uploads into IM and our maintenance repositories, parts catalogues, 1 to 200 general arrangement design, and a 3D model of the as-built track as well. 3D scanned layout at installation. That's using and also providing geometry verification and evidence within the ITP. Standardized installation and maintenance tasks. The BIM model with all the data from pre-installation and agreed maintenance tasks. There may even be costings in there to say how much the thing costs to install and how much parts cost as well. So you can actually get a cost model from it. And then that's handed to the maintainer and available to access via the asset register. And under maintenance, we're using all of our sort of fault condition monitoring systems, reliability focused pattern recognition, not just safety focused, but reliability as well for S&C. Digital twin with predicted replacement assessment, telling us when to actually replace parts. Dynamic autonomous geometry and rail profile inspections, so we can do that dynamically for the actual overall geometry and rail profile. So we can do 053, 054 dynamically. Site-specific track behavior monitoring. And then there's the embedded sensor side of things as well, applying RFID tags to areas where we know we've got concerns, and then not forgetting sort of earthworks, drainage, and sort of formation as well, and looking at that side of things. So I guess that's the inspection process. Now, what I'm going to do is just take you through some of the sort of lessons and some of the things I was involved with New York City Transit in terms of sort of reliability and S&C inspections that we did. So yeah, these pictures are of the elevated sections. We spent a lot of time on the elevated sections and also in the tunnels. So most of the actual network is, I'd say 60% is elevated section. About 10% is ballasted, and then the rest is tunnel. So these are sort of sleepers, or what they call ties, directly mounted to the girder structure. They've got a lot of guardrails, they've got walk boards, they've got braces. The cant is actually achieved by increasing the depth of the sleep or the tie. So you've got a wedge of a timber creating the planer and the cant. They're not packed. It's not the structure is not, the structure is completely flat. All track is jointed, so it's nicely moving in the sun and in the cold. The steel girder construction is sort of 1912, and the POE and the S&C designs are of a similar vintage. They're pretty old and pretty archaic. The middle picture there sort of shows a housetop. Let's see if I've got a picture. So this slide just gives you, this is Myrtle Avenue, again on an elevated section. And this is sort of highlighting what a housetop is. So this housetop is that sort of plate of very strong alloy steel. And it's basically there its original intention was to reduce wear of the switch rail, but it actually does provide a safety function. It stops flange climb derailments as well when you've got worn switches. So it does provide another function there. They're installed in all facing points on the turnout route. They do introduce reliability issues because there's lots of rubbing that goes on underneath and obstructions that you can't see. It sort of hides a lot of sins as well. The switch rails are £100 and £115, or Vigno or Rima. Base plates are sort of semi-fabricated base plates and slide plates. And the point machines are sort of, they're over 70, 80-year-old designs, and they're electric and pneumatic. So we tackled this by doing some reliability inspections. We didn't just look at safety and measurement for gauge and so on and things, they're the things that everyone does under standard sort of procedures. So we looked at it in terms of what the common failure modes are associated with all their assets, not just S&C, but S&C and track. We then aligned an inspection that considers the reliability condition rather than the safety condition. Safety inspections were still being undertaken. We didn't stop those. We looked at the inspection techniques used. We also did an explanation of wheel-rail interaction in switches, how that affects reliability, how you can get switches stalling and detectors starting to break and fail. Introduction of step gauges. We looked at introducing sort of step gauges for measuring slide plate gaps and switch to stock rail gaps. We then helped them determine the root causes and also looked at sort of a reliability inspection form. So we created a form and then we did the training. So we trained around 300 people. We also looked at introducing some reliable products that provide better reliability. So things like Interflon on slide plates, hard lock nuts on some of the jam nuts that kept backing off, and hard lock nuts on fish plates. And we also looked at sort of spike fast was being used and sort of those sort of fast patch sort of repairs, but they weren't using it correctly. So better guidance was given there. And we also did some sort of insulated block joint varnish. So we noticed they were using this paint, so we used a better varnish, and we also sort of advised on better coach screw systems and other things that would sort of improve reliability as well, which were approved, trialed, approved, and adopted within New York City Transit. We produced sort of a guidance on how track condition can affect signal reliability in S&C, some S&C, and even in just some plane line points. We did a plane line track circuit course as well, that showed how reliability of the track affects the reliability of track circuitry and signal circuitry, you know. So we did a similar training course there, and we looked at sort of how the track condition, so with its avoiding structure, how that, you know, how that can affect signaling. So high vertical acceleration, we've got a lot of vibration on these track structures. You can hear it from the ground, and you 30 foot up, and you can hear that vibration as trains go through. And that can affect things like tracks, circuit controller boxes, so the commutators with the point machines, the rods, the switch foot, which is like a pin that's on the front of the toe, and the pole changer, which is it's a way of sort of changing the direction and the polarity of a point machine to sort of switch the points over. A lot of these things are failing, and that was down to sort of vibration, you know, of the track. They used an old heel joint design, which we sort of stopped using about 60 years ago, but it was still there. And we sort of provided new designs that would remove the heel joint, but in this instance, it still existed. And you can see that the heel joint, some of them tight, some of them wide, but it did increase the pressure on the contacts on the point machines, and the clutches were also, you know, whirring away. Rods were misaligned. There's you know, other things were done to sort of try and counteract it, but they just weren't the right solution. And locks ultimately wearing within the point machine as well. Poor vertical alignment, well, that's slide plates. That's where we sort of introduced Interflon lubricants, and we looked at also rods and other things that were rubbing, making sure that you can provide better clearance for those. Poor face up. So face up is their RSO. It's how the switch rail sort of faces up to the stock rail. So we gave them some better guidance on that, because they didn't measure that at all. They only measured it at the switch tip. They didn't know that affected the flangeway, or that you know, flange back contact can be a result of a wide residual opening at the heel. And then obstructions, all sorts of obstructions. If I go back to one of these photos actually, so that's a basket just there. If you see that switch stop, next to the switch top is a basket, and that basket basically, so down here is this is Avenue A. I think there's cars sort of flying down here at 40 mile an hour below. So the last thing you want is lots of bolts falling onto cars. So these baskets basically capture anything that falls off, and they're in most of the cribs around the switches to capture any of those missing bolts or flying bolts. But there's lots of damage each year sort of occurred by things falling from the track, including tools as well. I did actually almost lose one of my step gauges. Luckily, it caught in a basket. So yeah, so water ingress is a huge problem that they do suffer in the tunnels as well, where switch machines were causing to fail because of that. And this is some sort of flange back contact. We explained to them about how reliability can be, you know, affected by the point rail, which acts as a guide rail as well, feeding that back to the point machine and so on, so they can understand that. And the last thing we did, So they did have remote condition monitoring on some point machines, but we did have our own fluke meter, which allowed us to go into any SRE or any SER or relay room, and we can either do it at the point machine or do it at the relays, and we can actually do a current draw over time of the switches. Make sure you pick the right relay and make sure you don't knock the relay out as well, which is the other concern because it is a live railway we're doing this on. So you've got to be very, very careful. But what we were able to do is to then monitor the switches from the relay room or from the point machine itself. We're using a sort of similar method you do with remote condition monitoring. It's not probably as accurate, but I'll show you one of the this is one of the graphs or traces we got from Grand Central Station. So Grand Central Station was a site that we had Interflon on, then we changed it. So it had greased slide plates, then we changed it to Interflon, and we were looking at the before and after effect to see, you know, if the current draw was reducing, and in this case it did. But what I'm just sort of showing here is these are the phases of switch movement that you see on the current draw. So you see that initial current inrush within sort of clutch setting range of the point machine, whether it's a Model 3 or a Model 5. So you need to make sure it's within that range. Then you have the unlocking phase, and then you're on that driving phase as the switch moves along. Then you can start to see the locking phase as a jolt as it's sort of hitting the other stock rail. The current then draws off, and then you've got the switch is locked in place. So what we did find, if we had a sort of a long wavy deviating line that deviated, and I'm talking about sort of quite high peaks and troughs, then that really signifies that you have got a friction issue. You've got slide plates that are binding, and so, or it could be a track obstruction because there were lots of rods that were binding against bearers and ties and so on that we were picking up. You could see visually, but you just didn't know how much it affected. We then go in and try to sort of fix it. We can move the bearer slightly, or notch the bearer, or do something with the obstruction to try and remove it. And then we used to do traces afterwards just to see. So we also did a similar system on pneumatic as well. So we did a pneumatic draw, if you like. So it was basically air pressure over time on the pneumatic systems. Not as accurate, but it did give you a sort of very similar sort of the phase of movement of the switches. But there are other things that come into it, like how you set up the pressure valve as well. So I think that's really, that is the end of my presentation. So sorry for running on a little bit longer than I probably should have done. This should have taken about 50 minutes, but it's taken about an hour. So yeah, I don't know, Colin, if you want to go into some sort of question and answers, I'll just stop sharing this.
Yeah, well, first off, I'd say what a superb presentation. I was interested to see with the S&C, you're embracing modern technology and using inspection trolleys and drones. I mean, the visibility and the clarity of the cameras when you were zooming in was absolutely amazing. So yeah, very good. I've got a couple of questions in the chat. I'll just read these out. If anyone else has got any questions, if you want to put them in there, that would be great. This is from Phil Edwards. He's asked, how are the critical S&C dimensions measured, such as gauge, flangeway clearances, etc., using the data from the drone surveys? And then he goes on to say, are they measured manually using a cloud survey in model space using the measuring tools in the software, or are these measured automatically by the software using recognition techniques previously pre-programmed?
So that is a good question. So that this is all done manually at the moment. What we did was we set targets to a measurement point on the S&C itself, so that the drone can see that measurement point and take it from that measurement point. The relationship between the top of the rail and the 14mm gauge strap, that was done automatically by the algorithm that I showed you. So the algorithm did that, and it did that height relationship between crown of rail and the datum point on the rail. But we had to put an identifier in there to sort of say this is where you need to measure from, and that's the point where we measured. So we had to either put a mark on there so that it could go on, and you're right, it wasn't actually going through, there's a mark, dink, there's a measurement. We had to go in and physically measure that mark, so we had to go in and analyze that system. and it's not that it can't be done, it can be done. It's just that for this, I guess, for this development project, we didn't have the time to create that software that then picks the point, tells it where to measure, and then develops a whole, you know, like Felix does. Felix does a similar thing. It tells you where to measure at and so on. And TEF forms are very precise on where you should measure. So you've got those fixed repeatable positions where you measure, and that's what you want to do. So we're able to do that by marking those lines, and then those measurements were taking off of it. And in most cases it was done as well longitudinally, so you can pick a longitudinal position, a fixed position, and say longitudinally, say 1.25 meters from the there could be a datum marker that sets the toes, and this is how some S&C is done. They put, so with Felix and others, some systems, they put a marker down, and what the trolley does, the trolley sees that marker, and then from that point there, it's sort of like, it's got a tachometer, and it tells you where you are in the switches. And if you say at 2.3 meters, you measure the gauge, then it will do that. So you can tell the drone to do that as well from a ground control marking position. We didn't do it on this, but we know it's possible and can be done. So this was done manually at this stage, but yeah, but it's all doable.
Good stuff. I have another question here. Are you able to compare dimensions measured which were taken in the pre-assembly depot compared with the installation on site dimensions on completion of the works?
So unfortunately, and that would have been a good thing to do for us to go out. I think that was installed somewhere near Fleet or Hook. I think it was Hook, one of those. So somewhere down on the southern. Unfortunately, we weren't able to go out on track. Well, one of the drones we used wasn't fully approved for track use anyway, or wasn't part of their normal sort of setup. But we weren't able to sort of follow up on that. Would have been a good thing to do, and then we could sort of analyse, you know, what they've measured on track, what their as-built show, and what we measured back beforehand. And that's something really that they should take forward for into track 3. I think is just making sure that the installed track. So I guess what we did with the BVI, also with the BVI, the install track at Mount Lens, the old sort of CV or BV turnout, we did do an inspection on that. So that's obviously under maintenance, and we did a comparison between what the drone saw on that. And again, that was within 1.5 mil. But no, we didn't go out to the installation and do that. Would have been good to do that though.
Yeah, thanks for that, Darren. That's really great. Great presentation, by the way. But yeah, I'm working on HS2, and it occurred to me that we could do this on HS2. That, you know, we could do those, take those dimensions like you've done when they're pre-assembled, and then compare them to the installed one. And we wouldn't have any restrictions on using a drone on HS2, because it will be Greenfield Railway. So yeah, yeah, great idea for us. It will really help us. Yeah, quality inspections. So yeah, I
think the biggest problem, Phil, is you've got a contractor using a different survey methodology or instrumentation. You know, then you've got someone checking it using a pole with a tape. Then you've got someone using a platform gauge. Then you've got some. We had this with PTIs and things. It's like, you know, we need to have the same surveying methodology and system throughout.
Probably the same drone as well.
Same drone. Yep. Yeah, exactly.
So yeah, I mean, we got the opportunity to do this because our track contractor will be doing both. So yeah. And
I know with Network Rail, there is continuation of this work. There are actually Swindon, I think, are using drones to do, and they're using a lot of live footage. So they're sending drones out, so they're not using it to do detailed measurements like we did. So most of ours was to see how accurate can we measure gauge and other things within S&C, you know. So they're more looking at the BVI side of things. Can they do a patrol run? Can they do an S&C sort of BVI with it, you know? And they're looking also at it live, but then they've got the data that they can also go back to later as well. So some people they've got sort of different applications in the way we want to use it. You know, it does take a day to process that data, because that data is a lot of data, and it's in the cloud then. But then, like I said, you then can analyze between 3 or 4 different visits, and you can do that sort of shift change between the two, whether it's a seasonal change or maybe they installed a new stop and switch at the weekend, and then you want to go back. Well, how is it compared to now? You know, is it miles off? So there's lots of other maintenance uses there. Yeah.
I guess you're using Flamin and Craven to do the drone survey and to also process the data
Yes.
before they gave it to you as a model.
Yeah, so
Yeah.
you've
Okay.
got a bit of IP there. They control that data. They control the algorithm. The algorithm, you've got to be careful that they're not taking something out that should be there. That they've got to make sure they're on the side of caution and safety when they do produce algorithms, because that's the thing you've got to be aware of. And I think with but Clam & Craven already had that portal. They already did a trial before. There was access there to this trial. That web link there, anyone can go onto that, and see what those measurements, because they made it available to anyone just to see that this is what we can do. So you click onto that link, and it's not just me that has access to it, everyone else does. And it just demonstrates the sort of the technology they have. But
sorry to stop you there then. Could I possibly get the link to that then, if it's freely available to anybody? Is that something you could share with us?
Yeah, it is.
So I'd like to show that to other people on the project and just show what can be done,
Yeah, definitely.
Yeah.
I'll see if I can put it in the chat whilst I'm on, and then by all means have a go, see if you can access it.
Because I think other people on this call as well might want to play around with it and have a look at it if you can do.
Yeah, definitely.
And you don't need any special software to do it. It's all there online. Yeah.
It is. It's all there online. Yeah.
Okay, great.
I'll just copy it now.
So if we look at this modern technology and everything it's bringing to the table, access to a wide source of information, as I said earlier, the visibility, the clarity of detail, is there any drawbacks to using, or any restrictions to using this system?
There is currently for drones. The drawbacks are you need good line of sight. You need clear days. If it was raining, then you would get issues with the water on the rail surface as well as the water droplets in the air, because it relies on optics and it relies on those sort of reflection of light is a big problem for drones, because it's photogrammetry basically that you're doing. So that's one issue. So on a cloudy day when it's not a lot of light, that could be another issue as well. So there are quite a lot of drawbacks still with drones. But having said that, there are drones that are getting better that can actually work around that and can work. They've either got better light imagery and other systems that they're working on where they can actually get better. But they need to know, what is the business take for this? What is the scale of it? Does everyone want a drone? Is it worth us developing something? Do we need 20 drones for the whole of the network, for every depot? Do we, so it's putting that business case together. How much money do we sort of spend on this, developing something that either the maintainer or the installer or projects need, So, and the other drawback, I suppose, is can they see what the human can see? And the processing time as well. So of course, when we see something, we can act straight away because we see an unsafe condition. But the drone, yes, it goes into the cloud then comes back down, and it's a bit like what we get from new measurement train and stuff like that. So if you can get an immediate response there and then and pass that on, that's great. But if you've got to wait for that data to be processed, then there is a delay in that. So that's the drawbacks, I guess. But they're trying to improve those things and trying to make it better and remove the need for people to actually go on site. Especially after the accident and the fatality at Surbiton, where an S&C inspector was killed. That the need for drones has become, or a way of inspecting the S&C without attending track has become even more important. So I think a lot of routes and regions are sort of looking at this themselves. Us in technical authority looked at it from I guess we had to do a proper, so we want to know, can it do basic visual? Can it do supervisory? Can it do all of the other things we do in terms of measuring within S&C? And to what level are we at the moment? And that was the main sort of, I guess the main output of that project.
Good. So I guess with the advent of technology, like we've seen with mobile phones, things will improve and get better. So I think the obvious thing is standardization across the network. So so good. Darren, that's been fantastic. Phil, could I just ask you to do the vote of thanks, please?
Yeah, sorry, I was on mute. Yeah, sure. Yeah, no, fantastic presentation, Darren, and a lot of information packed into a short space of time. And yeah, I mean, it's great for me as an old head, really seeing all this new technology really playing its part in helping us with inspection of S&C and controlling the quality of installations of S&C. No, it's brilliant. Yeah, great presentation. Thanks for spending the time to talk to us, the Ashford section. Yeah, on behalf of everybody in the Ashford section, thanks for coming and doing the presentation.
Brilliant. Thank you, Phil, and thank you, Colin, and thanks for having me.